Okay, you guys, now I gotta slow down. Here's where the work is. I think to generate Q2, it's merely going to be nothing more than P2 minus the projection of P2 onto my first Q1. All divided by Q1's magnitude twice, times my Q1. And in particular, I think that's going to give me, let's see, my P2s, I don't remember, I made it up again. X squared minus x. Minus the inner product of P1 and Q1. But I think the inner product is going to be 1 times 0 plus, oh, I get a little lucky here, don't I? It's just going to be 0. Shoot, that's too nice. Guys, so I can make this more interesting.
Didn't you define your inner product though with sigma notation?
Oh, good.
So wouldn't you want to?
I was assuming you didn't catch it because my example is too simplistic. I'm sorry to do this to you guys, but do you think we just make one small change in here?
Sure.
Can I change this to an x? Because otherwise they're already orthogonal to each other. I made the example up out of thin air. It's too simplistic. Can I make my change over here?
Mm-hmm.
So I change the first one to an x cubed plus I said x. So let's compute the inner product of my P1, excuse me, I misspoke. Let's compute the inner product of my, what are my labels there? P2 in my Q1. That inner product is 1 times 0 plus 0 times 1 plus 1 times negative 1. Is that okay? Why did you get so quiet? I'm not doing it right.
Yeah, you've defined your inner product in sigma.
I think I defined a whole new funky inner product. If I expand this out, you guys know what it looks like? Isn't that just an A sub naught, B sub naught? Plus, is that a 2 times A sub 1, B1? Is that plus a 3 times A sub 2, B sub 2? And finally, plus a 4 times A sub 3, B sub 3. Did you guys see my point?
Yep.
All right, now I won't make a mistake. I think the inner product evaluated on these two B's is going to be nothing more than, is that going to be a negative 2?
So in your sum, did you write i's starting at 0 instead?
Yeah.
I sure did, thank you. I'm sorry I'm such a mess today, you guys. Did you see Daniel's point?
Yeah.
I mean, by definition, I'm going to start with I being equal to 0. My apologies. So, would you guys, do you agree that the value of the inner product is going to be negative 2?
Mm-hmm.
Tell me if you don't. All divided by the square of Q1's magnitude, but when it comes to Q1's magnitude, where's Q1? Oh, it's right here. So square root of 1 plus 1 is? Square root of 1 plus 1 is? I think another mistake. Remember, even with the computing the magnitude, I still got to use my new funky inner product. You guys can see my point. So I think the evaluation of P1, or excuse me, Q1's magnitude, same thing as P1's, is going to be nothing more than, anyway, shall I sit? Oh, that's not what I came up with. That's because in my head I did something wrong. Shoot. You said square root of 6? I agree. I didn't know what to do because I was doing everything incorrectly. And Q1's nothing more than what I found above. So shoot, you guys, in the end, I guess I got nothing more than x squared minus x. Is that a plus 1/3 times x cubed? Plus 1/3 times x. Or shall I say I've got a 1/3 x cubed plus x squared?
So,
I'm listening.
where you got root 6 for your magnitude, did you took the magnitude of the inner product, which is defined as such, and that's how you got root 6?
Yeah, I evaluated the inner
Okay,
product of
okay.
those two pieces.
Okay.
You guys, do you think I can check to see if I made a mistake? Not that I'm done, I still need to find a Q3, but it's just that, to check to see if I made a mistake, I'll check orthogonality. With these two vectors, Q1 and Q2, let me just look at their inner product. 1/3 times, 1/3 times, 1/3 times, good, 1/3 times 4 is 4/3. Plus the product of these two coefficients. It's going to be negative 2/3, but I multiply by 2. Well, that means negative 4/3. So 4/3 plus negative 4/3 is. So far, so good. No mistakes. I do not think I'm done, however. So if you guys don't mind using my eraser to give myself a little bit more room. I think defined by Q sub 3 is simply going to be my P sub 3 backed off by its projection. Well, that is to say, is projection onto U1 bar. Sorry, U1 in this case is going to be Q1. Over Q1's magnitude twice, times Q1. But I also have to subtract off from P3 the projection of P3 onto Q2. All over Q2's magnitude twice, times Q2. Well, let me put in my functions. P3 was, I have to do Q. Oh, here it is. So P3 is going to be nothing more than x cubed plus x squared. I'll subtract off P3's projection, P3's inner product with Q1. But here's my P3. My Q1 is nothing more than P1.
Be negative 2, right? Oh no, that's 2 in Q1.
So I go with 2. Do you guys get the same number?
Yeah.
All over Q1's magnitude, but haven't I already computed Q1's magnitude?
Yeah, it's root 6. Yeah.
Times Q1, which by the way is the same as P1. Minus the inner product of P3 with Q2. Okay, now I gotta slow down. Here's my circled Q2. And here's my P3. I'm being honest, you guys. I gotta figure out what the other product is. Hoi, hoi, hoi. Is it 13/3? It's an honest question, all right? Does anybody agree with me? You're shaking your head. Well, let's generate it. I think the product of the x cubed factors are going to be the product of 1/3 and my 1. Oh, but shoot, I got to multiply by 4. I got to add to that the product of their coefficients of x squared, which is 1 times 1. Oh, times that, 3. And I think it's going to give me 4/3 plus 3. Now, do you guys believe my arithmetic? Mike?
I'm curious where the coefficients 2, 3, and 4 come.
Say it a little bit louder, I'm sorry.
Where did the coefficients 2, 3, and 4 in the inner product, how you defined it after the sigma limitation?
It came from the fact that if I is equal to 0, I get a sub naught times b sub naught times 0 plus 1, which is 1. But when I is equal to 1, I get a sub 1 times b sub 1 times, well, when I is 1, I get coefficients of 2. Do you see how the coefficient out front is just 1 more than how far in and out on expansion?
And why does there need to be an I plus 1?
There doesn't. I made it up out of thin air. I said, I know I've erased it, but I said where we will define this inner product to be
Okay.
this. So I'm the one who made this inner product.
Okay, so it's in the directions it would be mentioned that it's
Yes, I've got a whole new funky inner product to define. And by the way, you guys, I didn't check to see if it's an inner product, but I just did. It works. It satisfies all 4 axes.
I keep getting 4 for the inner product of P3. Yeah, I give him something.
Oh, did I make a mistake? I'm so sorry. Let's check it. Here's my P3. Here's my Q1 or P1, they're the same. I come up with 4 times 1 times 1 plus a bunch of zeros, which is 4. What did I say it was?
2.
I'm so sorry. My mistake. I stand corrected. So if you guys are okay with my arithmetic, let's divide out by Q2's magnitude twice. But to come up with Q2's magnitude, I forget what Q2 is. Guys, can you help me with this one? I think the magnitude of Q2 is going to be nothing more than the square root. Is that a 4 times 1 9? Plus 3 times 1. Is that a plus 2 times 4 nines?
Can you explain how you got 1 9 and 4 9s?
Yes, can I erase it? I really meant to say this. I've got 4 times the coefficient of x cubed twice. Plus my 3 times the coefficient of x squared twice. And then finally plus 2 times, well, the coefficient of x twice, which would be 2/3 times 2/3. I know I made a sign error, but I made it twice, so it doesn't matter. And I think in the end, that's going to give you fractions whose denominators 3, whose numerators, I have no clue. Yikes. It's at 39. Again, you guys just double check my arithmetic. So I suppose that the denominator's fraction really is going to be 39 over 9. And I'm going to multiply by Q2, but I still forget what Q2 is. Instead of 1/3, you guys help me with this. 1/3 x cubed. What's the rest?
Plus x squared minus 2/3 x.
Is that it? All right, here too, you guys, I have to apologize for my example being so simplistic. I got really lucky. Those two fractions the same.
Why is it the same? Why is the bottom not root 39 over 3?
Because it's squared.
Because I squared it.
Squared.
So I get 39 over 9. I just reduced a fraction. But I really did get lucky. Particularly with an example I made up out of thin air. Can I erase my root? And everybody, in the end, I suppose what that really means is I've got nothing more than x cubed plus x squared. Okay, I'll slow down with my arithmetic at this point. Is that a minus 2/3 x cubed? Is that a minus 2/3 times x? Minus a 1/3 x cubed minus x squared plus 2/3 x. Or shall I say, I've got this many x cubes, 2/3? No.
0.
Oh, I get none. Jeepers. How many x squareds?
0.
They completely drop out. How many x's?
0.
That's a problem. Oh, shoot. You guys, what I'm doing in my head is I'm checking the original vectors. I wonder if I accidentally came up or created a set of vectors that themselves are following. But I didn't. You guys, is there an arithmetic error I have somewhere in here?
Does it have anything to do with the third one? Is a combination of the first two?
Well, that's what I was trying to check. I didn't come up with a combination in my head.
Isn't it just add the first one to the second one, you get the third one? So x's cancel out and you get x cubed plus x squared.
Oh, that's it. You know what I'm trying to do? I'm trying to check orthogonality, not linear independence. All right. See, guys, what happened in the end? When I created this basis for a subspace of P3, it's not really a basis. It's not an efficient span space. Because this one is a duplication of these two. It's a combination of the first two. It was not a linearly independent set. So my technique is fine on the ink board. I didn't do anything wrong. It's just that my example was a little simplistic and that everything dropped out because in reality, I've got a vector space of dimension 2, not dimension 3. That's what happens sometimes when I come to class. I make up examples out of thin air. Usually they're more complex. This one became more easy. But you see the process, correct? What if I actually created an orthonormal set of vectors. So I went from a collection of people PIs, used this Gram-Schmidt procedure, created a whole new set of vectors. That not only is an orthogonal set, but orthonormal as well. In other words, whenever you take a peek at any two of these vectors with their inner product, it divides to 0. But because they're going to be unit vectors, I think the inner product of any vector with itself is going to be anybody? All right, let me state the question again. If I've got a collection of orthonormal vectors, then I think the inner product of any q sub I with itself is going to be positive 1. Because you can think of the inner product as the magnitude of q sub I with itself times the cosine of the angle in between, which is 0. But the cosine of 0 is just 1. And the magnitude of those two vectors is going to be 1 as well. They're the same vector and they're unit vectors. So I think with an orthonormal set, it is the case that the inner product of q sub I with q sub j is going to be, you guys be sophisticated, it's going to be what? All right, let me say that all over again. I said any two vectors that are not the same, any two distinct vectors in the set has an inner product of
1.
Any two distinct elements is going to be 0
Okay.
because we're orthogonal. But the inner product of any element, a set of q's with itself is going to be 1. So give me the answer. You know the second exam, the first exam you took? No, the second exam. Exam 2. 2. Smallest prime number. You're kidding.
2?
I don't understand. Q sub I, yeah, J is gonna be
Delta sub.
The identity matrix?
No, Kronecker delta notation that I used to define the identity matrix, but it still applies here, doesn't
What is
it?
delta sub I J?
I feel so alone.
I really need to bring in that picture,
Which picture?
the stress area.
So you guys, delta sub ij is, say it out loud, 1 if I equals j, but 0 elsewise. Otherwise. You're scaring me.
So are these examples too easy?
No, I like my second example only because I gave you a non-standard inner product. So I'm happy with my second example. I just apologize for choosing an initial set so easy, but at least we went through the process, see how we find the third one.
Could we tackle one that isn't in p-space?
Sure. So you guys, same instructions. I've got a basis for the subspace, for a subspace of M2. I want you to come up with a set of orthogonal vectors spanning the same space as the set B spans. But again, the vectors are going to be orthogonal to each other. Let me call those elements, these elements right here. How about A1 and A2? Then I'll come up with a B1 and a B2. Excuse me. I'm being a little silly with B1, aren't I? B1's just nothing more than A1. Gotta start somewhere. So my B1's gonna be my 1, 2, hold on, I said 1, 2, negative 1, 1.
Negative 1, 1.
It's just that my B2 is gonna be nothing more than my A2 minus the projection of A2 onto B1. Or shall I say, it's gonna be my A2, which has entries 3, 1, 1, negative 2. Minus, okay, I'll slow down with my arithmetic. I guess the standard product, inner product on A2, B1, is gonna be nothing more than is it 2? You guys double check my arithmetic. 1 times 3 is 3, plus 2 is 5, minus 1 is 4, minus 2 is 2. Now, I think when it comes to B1's magnitude, I think B1's magnitude is going to be the square root of, okay, here I go. 1 plus 4 plus 1 plus 1. So give me the square root of 7. And that square is going to be positive 7. Oh, but I'm multiplying by B1, which has these entries. So in the end, that's merely going to give me a 2 by 2 determinant, in which my entries, symbol by symbol, are going to be, is it a 19 sevens? Is that going to give me a 5 sevens? Then a 9 sevens? A negative 16 sevens?
The second term should be 3 sevens.
Which one?
The second top right.
4 sevens.
It's 7 sevens minus 4 sevens.
Yeah,
I'm so sorry.
3 sevens, yeah.
I agree with you. The 3 sevens. You know what, you guys? I might have made more mistakes. So let's check. Let's check orthogonality. And it's a piece of cake. I'm simply going to look at the inner product of my B1 and B2 and see what I get. I better get a 0 in the end. And looking at the inner product of these two pieces, that give me a 19 sevenths plus 6 sevenths minus 9 sevenths minus 16 sevenths. Let's see what I get. There's going to be 25 sevenths. Oh, here's negative 25 sevenths. I guess I've got no remaining arithmetic errors. It checks out. You guys, not bad, is it?
No.
It's just an algorithmic procedure I need you guys to repeat.
Is there anything that we, like normally when writing a basis, we like B equals, that do we write this as something? Like, is there any letter that we
No. I just fill out, I don't have anything special symbols for. I just fill out words. I consider this basis for a vector space.
and you just say that this is the orthogonal basis of the vector space?
Yes. Well, to be honest with you, if I asked you to apply Greenwich procedure, I would assume you've got that anyways. And if you're nervous, you made a silly mistake, you just check orthogonality like I did. Can I have you guys get practice with this? So, practice. I want you guys to dive into section 4.12, I think.
Yep, it's 4.12.
Stopping early?
Huh?
We're stopping early?
It's 1:40, right? Not that early.
1 through 9 odd. You guys, this was too nice. Can we look at number 10? (13 through 21 odd). 25. 27. 29. Okay, I'm happy.